Hey guys, we're going to do an introduction to 4.2, which is about Riemann sums. And we're going to use Riemann sums to approximate areas under a curve. Suppose you're asked to approximate the area under the curve y equals x. And our bounds here are the x-axis, the y-axis, and x equals 4. So what would this look like? We can draw the line y equals x. We know what that looks like. And we want to find the area under this curve between the x-axis, the y-axis, and x equals 4. So let's say this is 4. So what does this look like? Well, if you imagine this shape, it's simply a right triangle. And we know how to find the area of a triangle. In geometry, you learn the area of a triangle is 1/2 base times height. So easy peasy. This has a base of 4 and a height of 4. So in order to calculate this area of this region, you simply do 1/2 of 16, which is 8. So we can see that this area is 8 because that was a nice, easy geometric figure. But suppose you wanted to find the area under the curve of y equals x squared. Using the same boundaries given the x-axis, the y-axis, and x equals 4. So that would be given to you. They would give you your bounds of where you start and stop to draw your geometric figure. So first, the curve y equals x squared. Okay, we know what that looks like. It's a nice, simple curve to draw. But then when I go ahead and set up my boundaries to see what my figure looks like from the y-axis over to 4 and the x-axis up, we're going to get this shape that is not quite a triangle. It's not going to be quite as pretty as the last picture. It's kind of a triangular looking shape, but it has that curved part of x squared. So that's curved. That's not perfectly linear. So in order to find that shaded yellow region's area, we don't have a formula. We have to do something else. We have to come up with another technique. So the technique we're going to use is drawing rectangles that will fill up that yellow space. Obviously, the rectangles that I'm drawing here are covering more space than even the yellow space. So by calculating the area of each of these rectangles, I'm going to have an estimate of what the area in the yellow region is, but it's going to be an overestimate in this case because I'm clearly covering more space than just the yellow region. So this idea of making rectangles to fill the space is what you're going to be learning about in this video. So as you can see here, each of them has their own base and each of them has their own height, and we know that the area of a rectangle is simply base times height. So all we have to do is calculate the area of each of those, add them all up, and then we have an estimate of what the area under the curve equals.
Alright, in this video we're going to talk about Riemann sums. It's a pretty important idea in calculus, and it's something that actually leads to a huge idea in calculus. So let's see what we can do with it. So to start with, we'll just kind of describe the three that you're going to see, and those three are a left Riemann sum, a right Riemann sum, and then a midpoint sum. I'm not actually going to calculate a midpoint sum in this video, because they're kind of annoying to calculate, and you'll get the sense from the left and the right of what really is going on. So for a left Riemann sum, what we do is, I've kind of just divided this up into three. From A to B along the x-axis, I've divided into three equal parts, even though I did a bad job of that. And for a left Riemann sum, what you do is at the left endpoint of each interval, you find the height. So you go up to the value of the function, and then from there what I do is I make rectangles using those heights. So you can see I end up with those. So it's called a left Riemann sum because the height is determined at the left endpoint of the interval. You might then be able to guess what a right Riemann sum would be. So we have our intervals, and at the right endpoint of each interval I'm going to go up to the function to get a height, and then draw my rectangles based on that. And then for the midpoint Riemann sum, what I have to do first is calculate the midpoint, which I didn't really calculate, I just kind of put in. Then I go up to the function, and so that's going to be the height. So what I'll do in this case is I'm just going to draw in the top of the rectangles there, and then we put in our vertical line. So the midpoint Riemann sum is it's kind of the most annoying to calculate, really. Maybe it's a little bit harder to generalize. But anyway, for each and every one of these, I've made equal divisions. So I call all of those delta x. And so to calculate delta x, and this is important, it's always just going to be b minus a over 3 in this particular case, but it would be b minus a over n in general. So what I want to do is see what I can do a problem. So I want to approximate the area enclosed by f of x equals x squared plus 1, the x-axis, the y-axis, and x equals 2. So when you combine all those things, you get one region in the plane. So the first way I'll do it is I'll use a left Riemann sum, and I'll use two rectangles. So I'm using a small number because it's a little easier to calculate kind of in your head by hand. So let's create a graph, and then I need delta x. So that's going to be b minus a, so 2 minus 0, and then divided by n, and n is 2. So 2 minus 0 over 2, which gives me 1. So it's a left Riemann sum. So what I'm going to do is on each of the intervals, which actually from 0 to 1 and then 1 to 2 are the intervals that I want. On each interval, I'm going to use the left endpoint to determine the height of the rectangle. So there's at 0, I put in the height. At 1, I put in the height. I'm going to finish drawing the rectangles like that. So you can see this is going to give me an underestimate of the area. And now the area is approximately the base, which is 1, times the height, which is 1. So the height at 0 is 1, just plug 0 into f of x. Then the base is 1, and then the height at x equals 1, plug 1 in, you get 2. And so my approximation would just be 3. And I know it's an underestimate, but I'm not really concerned about that. The next thing I want to try is a right Riemann sum with n equals 4. So again, I'm going to have this picture, but now since n equals 4, I need to recalculate delta x. So it's going to be 2 minus 0 divided by 4, which gives me 1 half. So it's going to go from 0 to 1 half to 1, 1 to 3 halves, and then 3 halves to 2. And it's a right Riemann sum, so the heights are determined at the right endpoint. So from 0 to 1 half, I determine the height at x equals 1 half, and so on. So I've drawn in the heights at the right endpoints, and now I'm going to finish with the rectangles. And you can see I did a kind of bad job there. So the area is approximately, it's going to be 1 half, and then the height at x equals 1 half. So 1 half is the base, so that's going to be the same for all the rectangles. So 1 half, the height at 1 half is that, plus 1 half, the height at 1, plus 1 half, the height at 3 halves, and then 1 half, the height at 2. And then if I add all those up, I get that the area is approximately 23 over 4. Okay. The next question, I want to find a left sum, and I want to just use n rectangles, so not a particular number, just like in general. So let's see what I can do. So delta x, again, will be 2 minus 0 over n this time, which is just 2 over n. And now let's see how we can break up the axis here. So I go from 0 out to 2, so that final one is actually 2. And so that point right there is 0 plus 1 delta x. So it doesn't matter what delta x is. To get to that division, I would add delta x to 0 once. To get to the next one, I would add delta x twice to 0, and then I would add it 3 times to 0, and then I would add it 4 times to 0. And now what I want to do is jump ahead, so I'm going to dot, dot, dot. And here I would just add it n minus 1 times to 0. And since it's a left sum, the heights are going to be determined at 0, there, but I'm not going to include that one, so not this one. Alright, and what I want to do is I'm going to try to write a formula for this. So the area is approximately, it's a summation, so I'm going to say that I is what I'm multiplying delta x by to get each of these points. So in general, what I want I to first start at 0, right? Because that first point where I'm finding a height is 0 plus 0 delta x's, so I starts at 0. And then I don't include the last one, but I do go to the kind of, I don't know, the first to last, I don't know, next to last, let's say. So I'm going to stop counting at n minus 1. And then each rectangle will have a base of delta x and a height that's determined at that left endpoint. So that's going to be f of, and it's 0, which is the left endpoint, plus I delta x. Alright, so take a look at that, see if you can make sense of it. And then what I've done is, I have a table here. So for various values of n, so when n is 1 to 50 and 1,000, so 50 and 1,000, what happens here is as n gets bigger, you get more and more accurate. So when n is equal to 1, I just get 2, which is, that's not very good. When n is 2, I end up with 3. So that's by plugging into that formula, which I use a calculator to do. When it's 50, I get 4.5872, so it's bigger. And remember, we're underestimating every time, so it should just keep getting bigger as I increase the number of rectangles. At 1,000, it's 4.66267. Then what I did was I used my calculator, and I let the calculator take the limit as n approaches infinity of this area formula, which is a function of n. And the calculator spit back this answer, 14 thirds. So I would say that the actual area is 14 thirds, and I can approximate it by letting n get bigger and bigger. So what I'm going to do now is basically the same problem again, except I'm going to do a right sum. The right sum has certain advantages, which we'll get into. So calculate delta x. Let's take a look at this number line again. So it's essentially the exact same labeling scheme. So I get 1 delta x, and then 0 plus 2 delta x's, and plus 3 delta x's, and so on. So out to here, dot, dot, dot. So here is the 0 plus n minus 1 delta x. But remember, it's right endpoint, so I have to go all the way to the end. So this is 0 plus n times delta x. And if we take a quick look at that, n times delta x is the same as n times the quantity 2 over n, which is equal to 2, which is that right endpoint, which is what I wanted. So again, I'm going to write a formula. So those are the places I'm evaluating it. It's important to realize where you're evaluating it. I call those evaluation points. And we don't include that first starting point, which tells us what I is going to start from. So the area is approximately the sum from I equals, I don't include 0, but I start at 0 plus 1 delta x. So I actually is going to go from 1, and then I stop when I get all the way out at n. So 1 to n, and then it's the base is delta x, the height is f of, and then the evaluation points are all 0 plus I times delta x. So I get that, and I made a table again. So when it was 1, I just got 1. When n is 4, I get 23 over 4, which is the answer that I got previously when I did it by hand. 50 gives me this number, and then 1,000 gives me this number. So I'm getting overestimates here, so I'm approaching the answer, but still over. And then I let my calculator take the limit of this function again. And I'm pretty sure there's another video that shows how to enter that into your calculator and use it to approximate this limit. And again, it gave me 14 thirds. So it turns out that it didn't matter if I use a left or a right Riemann sum. When I took the limit as n approaches infinity, I got the same answer of 14 thirds. And that's actually the true area. So that's a couple of examples. I'm going to end this video here, and in another video I'll show you how to actually calculate that limit by hand, which, although you may not want to, is kind of an interesting exercise, and I think you learn a little bit by doing it. So I hope this was helpful, and good luck.